Hi, and welcome back to the old shop. This is a continuation of the last video, and this time we're going to attempt to find the missing dimensions in order to make a slide valve for this engine. And we're going to use a Bilgrim diagram, which was devised by a guy named Hugo Bilgrim back in 1870, and it's really a clever chart. And I was just going to say, if you're really interested in this, my favorite explanation of the whole deal with slide valves and stuff is in this little Odell's book. I got this on eBay, I think, and it's part of a 4-volume set called Engineers and Mechanics Guide, and this is book number 1. And it's laid out so that the average person can figure out what they're talking about. It's done in question form. Like it asks the question, what's a slide valve? And then it answers it. And then it asks a question like, what's the lap? What's the lead? Why is this important? What's the shortcomings of a slide valve? And then it's also got a very good explanation of the Bilgrim diagram, and it's sort of like what I use, or what I'm going to use. And so we're going to get right to that. Thanks a lot for watching. I really appreciate all the great comments and the subscriptions, and you can check my G Plus page. Once a week I try to put up something on there that's coming up, and so we'll get going on this right now. To start out with, to get the dimensions on the slide valve, we need to lay out the events as we turn the engine around so that we'll know where we're at. And the events are laid out along this line here at different points, but I'm going to use a pointer against the flywheel in order to find these events, to mark them. So I've got this chart here that will take into consideration rod angularity that we talked about in the last video. And what I'm concerned with is that this is the top dead center, this is the bottom dead center. This is laid out in 100% scale. These are the actual sizes of the things that are on the engine. And this, of course, has got a 6-inch stroke. So this circle is 6 inches in diameter. It's got a 15-inch center to center rod. So this line from these points up here is the rod length at 15. So the first thing that I'm concerned with is the steam. Well, the steam admission will be a little bit before top dead center, and that little bit is called the lead, and I'll show you about that later. But the steam is being admitted and the piston is coming down, and when we get to right here, which is 3/4 of the stroke, or 4.5 inches down the stroke, it's the cutoff. That's the point at which I want the steam to cut off. You don't let the steam go all the way to the bottom of the cylinder, because it was found to be very inefficient that way. If you cut it off at about 3/4 or somewhere along in here, the steam expands the rest of the way and then is exhausted. So I want the steam to cut off here at 3/4 of the stroke, and then the rule of thumb is to hit the exhaust port open at 9/10 of the stroke. So you got the steam started out the cylinder before it actually gets to the bottom. So I drew 15-inch rod up here, and that's the point of cutoff right there, which is 114 degrees by measurement from top dead center to the cutoff. And then after the steam is cut off, it expands, continues to expand till you get to right about here, and at 9/10 of the stroke, I calculated with a 15-inch rod to be 137 degrees. So this is the cutoff line, this is the release line. So I measured these angles, 114 and 137, and I transferred them to a Bilgum diagram. And this is the diagram here. And if you pause it, you can study the different parts of it. But basically, on an engine that already exists, you know some of these dimensions, and this is full size here. You can scale everything right off this diagram. Well, you know some of these things, and you're looking for some of these things. So you use what dimensions you already have in order to figure out from this diagram what the dimensions are of the things that you need to know. Okay, this is the Bilgum diagram for the Morris engine that I drew up, and the parts of it are the baseline here, and from this center point you lay off half a circle with a radius equal to the port width of the intake ports. This is a ×2 scale, then in order to make it bigger for you to see and easier to actually measure the dimensions off of. So the ports on the Morris engine are ½ inch, so I doubled it, and this is an inch. Then this outside half circle here is actually a radius equal to half of the eccentric throw. In other words, the whole eccentric throw is from there to there, so you take half of it and then you draw that radius there. This line here above the baseline is called the lead line, and that is the actual amount that the intake port is open at top dead center. It's a little like ignition on an automobile engine. You know, you want a little advance on it, so get the spark, advance to get the fire going before the piston rolls over top dead center. Well, it's the same thing with a steam engine. You want to get the steam moving through the ports before it rolls over top dead center. And in the case of our Morris engine, I decided it should be a 1/16 of an inch. So this is ×2, so that's an 1/8 of an inch there between there and there. So I laid off the cutoff line. I measured the angle on the other chart to know what the angle would be based on rod angularity, and it was 114 degrees. So I just made this line here 114 degrees. And then you got to fiddle around a little bit with your compass and find a point and a radius that will draw a circle tangent to three things: this cutoff line, and this inside port line, and this lead line. And once you get that circle in there, the radius of it is actually the outside lap of the intake valve. That is the amount that it sticks up above the port on the top and the bottom. And on this, after I divided this distance here by 2, it came out to 0.582 inches. So that'll help figure out where we're supposed to be. Oh yeah, one other thing. If you drop a perpendicular down all the way to the bottom here, this distance is directly measured to be the linear advance. And that the linear advance is the amount that the slide valve is displaced from its center position when the piston is at top dead center. So that really helps in knowing where the eccentric should be located on the shaft, and I'll show you how that works. Okay, I already have labeled the different parts of the strokes on the flywheel as they come by the pointer, and I did this by measuring down in the cylinder with a rule like this, I moved the piston down to a certain, like to the cutoff, and then I came over here and I made a mark. This is CO for cutoff, TC for top center, and the other marks are for the exhaust, which we'll get into a little bit later. But if you put it up on top dead center, make sure, yep, top dead center, my valve being actually longer than it needed to be, I made a mark right there where I can see the edge of that port just underneath the plexiglass, actually down a 1/16 of an inch from the edge, because that's the lead. Okay, so then I did the same thing at the bottom on the other top dead center so that I could adjust this valve and get it centered in there so that the lead is going to be the same. Okay, then at 114 degrees past top dead center, we come to cutoff, which is right there. And at that point, this valve is moving back up again, and it'll be in the same position it was to begin with, just with this line here just covering the port. So that line will be the edge of the port that I've got to trim this to in order to make the admission and the cutoff work out right. And you also at the same time are playing around with the eccentric. The eccentric is never keyed onto the shaft because you have to make adjustments to it. And it's got 2 set screws, it's big square-headed bolts here. So I've loosened them up and I've knocked the eccentric around a little bit as I was making these lines up here to kind of, if you don't have if the cutoff is too late, if the cutoff is too early, you need to make the slide valve a little bit longer, but then you have to go back and readjust the eccentric so that the lead stays the same. That's basically what I'm trying to say. Okay, so that works out for the intake. And this line here that I scribed on the side of the cylinder is exactly at the center of the ports. And if I put this right on top dead center, that distance that distance from the center of the valve, from this line scribed on the center of the valve up to that center line of the center of the ports, is the linear advance that's on the chart that I just showed you, and that's actually 0.644. I measured it and it's pretty darn close. So I know I've got the eccentric right. Okay, so now we got the intake figured out pretty good. We got to deal with the exhaust, and that's just a matter of knowing how much inside lap the exhaust cavity has got to have on the back side of the valve over the port width. And the way you find that is you draw the release line, which is at 137 degrees after top dead center, and I measured that off of the other diagram to take into consideration the rod angularity, and you construct that line up through there, and then you put the compass again with a point on this same line as the intake circle, and you draw a circle tangent to that line, the release line. The radius of that circle is directly measured to be the inside lap of the exhaust cavity on the back side of the exhaust valve. And after dividing this dimension here by 2, because we're at a ×2 scale, it was 0.168 inches. And so that'll help us figure out where that exhaust line is going to be on the back side of the D-slide valve. Okay, working through the strokes, we'll start at top dead center. We get to the cutoff on the intake, and we roll it up a little bit further, and we get to the release on that stroke, which is on the X here. At the release, I don't know if you can see it, but the port, edge of the port behind the plexiglass is right there. So I'm going to make a little mark over here and label it R. That's the release, and that's going to be the top edge of the exhaust port on the back side of the slide valve. And I've turned the cylinder back to the end of the exhaust stroke where the release mark is closing up on the what would be the cavity on the back side of this, and you can see it's that far before top dead center. That's the cushion where the steam is being compressed. The exhaust is closed off, and that steam is trapped in there. And for that distance, it's compressing the steam in the top part of the stroke and cushioning the piston and the rod and everything that's traveling up from coming up against the top, and it makes it a lot easier on the components. That all steam engines are designed with a certain amount of cushion in there. Now I've done the same thing for the bottom half of the cylinder, and I've marked the release point. And when I bring the release point back down to close the exhaust off, and come over here and you look, there's only this much cushion on the upward end of the stroke. And that's because of rod angularity. And it's really the only dimension in the whole valve layout that is thrown off that much because of rod angularity, and that's because it's an event that happens fairly close to top dead center. So that's where rod angularity makes the biggest amount of difference. So I've only got about that much cushion on the upstroke, and we had about that much cushion on the downstroke, even though the valve openings were correct. So you'd like to have a little more cushioning on the downstroke because you got the extra weight of the piston rod crosshead and piston rod and all of that stuff coming down. So you'd like a little more cushion on the bottom. But all things considered, the Bilgrim came out pretty good. It's just a matter of, say for instance, the Bilgrim was what they were trying to do when they built the engine, but when it actually got built in a production environment, the port spacing wasn't exactly what they wanted because the casting, you know, it's pretty hard to cast these ports in here and hold those cores in the casting molds and get the spacing just exactly right. And if they aren't just exactly right, the edges have got to be ground or filed, and you know, they're in a hurry. What's good enough? So I'm not surprised that it's a little off, and I don't think it makes that much difference anyway at 250 RPM. So when the dust cleared, I measured the marks with a caliper and came up with these dimensions. It's kind of amazing how it came out to whole fractions, but there it is, plus or minus 10 thousandths. This is the material for the slide valve. It's a piece of cast iron, grade 40. It's actually bar stock, and I'm going to square it up in the shaper. I've got it drawn out roughly here. It's 3 7/8 by 5.245. So I made a couple of trial cuts on each side to make sure that my vise was level and straight, and it's within 1,000th or so of the same thickness this way. I still got about 300 to go on that. So to set up this machine, this is a G&E shaper about a 1925, and they used to put these really slick little gauges here to tell you what the stroke is. So what you do is you run the ram all the way back to the back end of the stroke. Then you come out here and you say, well, we'll give it 3/4 on each side. So that'd be about an 8-inch stroke you want. So on this shaper, to set the stroke, you loosen this knurled knob here. And then you crank this in or out. So you put it on the 8, tighten it back down again. Then you have to adjust where that 8-inch stroke is going to be over your piece. And I want about 3/4 of an inch off the back end. So you loosen this up, and then you can crank this up to then about 3/4 of an inch at the start. Crank it back down again, and then you can just quickly check it. So I'm overhanging by about an inch, so that's really more stroke than it needs, but it'll be fine. I have a rounded nose roughing tool here, and I'm probably gonna start off with, I don't know, about 30 thousandths or so, just to see where we're at. right there is 75 thousandths cut, 20 thousandths feed. With the shaper putting the intermittent load on the shaft, you can hear the governor chasing it around, trying to keep the speed steady. Before I make any finish cuts on this, I'm going to reset it in the vise. This is not exactly the greatest way to hold something in a shaper, because with heavy cuts it can move around in there a little bit on you. So there's no other way to do it with this size piece. So do it. 3.880, 5,000 total. Close enough. This is a lot shorter stroke on this side, so I can run it at a higher speed. Alright, here it is blanked out in these two dimensions, and I'll resurface this later. I think right now what I want to do is get the whole board down through the middle of it for the valve rod. So that's going to be 9/16, which is the valve rod diameter, plus a 64th for a little clearance. I'm going to show you how to lay this out with an old height gauge. And I don't know how old this one is. Not an antique, but these height gauges have been around for a long time, and most all of them, of the old ones, worked with a vernier scale, and they were really very accurate. Now this is measuring the distance from the bottom up to this flat part of this point, and I want 1 inch 11 thousandths. So if I can get this to focus in here. I started with 1 inch with the 0 right across from the 1, and then I raised it up using this knurled knob for fine adjustment until the 11 on this scale just lined up with a mark over on this side. It doesn't matter really which mark it is, but you can see the 11 right there is lined up with a mark, and the mark above it and the mark below it are obviously not right. So that right there is 1 inch 11 thousandths. Trying to see a brand on this. Here it is. Brown and Sharp. Okay, we chalk this up with some soapstone. See that line there? So now I'm going to find the center using a hermaphrodite calipers. During World War II, my father worked at a defense plant in Johnson City, New York. It was Remington Rand, and they made propellers for bombers and big fighters. And he told me that was the most interesting job he ever had, and he was actually the night tool room supervisor, and they had nothing to work with because of the war being on, so they had to make everything. And one of the first things he made was a set of these hermaphrodite calipers, and it's got his initials stamped on them here. And I use them quite a lot. And a quick and easy way to find the center here is to just estimate it and then come over this way, and it's got to go a little bit bigger. Put a line there and a line there. Come out a little bit more. This never really goes good when I'm filming. Well, you end up with two lines that are very close together. Take a punch. Never center punch anything on a surface plate. And that's the center point. Now this is cast iron, and you normally would not use lubricant on this, but it's a long hole, and when you're drilling long holes, you can expect everything to go wrong. That's more just to lubricate the drill than the cutting edge. I think the fit in the hole is about right. I may have to open it up just one more drill size, but you can do that anytime. Next time I'm gonna surface this in the shaper and start lightening the profile and test fit it in the engine. Thanks a lot for watching. I appreciate all the comments and the subscriptions, and we'll see you next time.